So here are the answers to part 2 of the investigation. Take a look at the first example right here. You can see that the curve is smooth everywhere, so it'll be differentiable from 0 to infinity. I left the 0 off because technically curves aren't continuous at their endpoints. When you come to the next one, the absolute value function, it's differentiable everywhere except for at the cusp, which happens here at -1. Therefore, I think the easiest way to write this would be to say that the domain on which it's differentiable is all real numbers except x cannot be equal to -1. If you wrote it this way, that's fine too, but I think the first one's a little easier to think about. I'm going to use that kind of notation, the set notation, on the next example. Okay. Here we've got a rational function, and it's not differentiable at the asymptotes because it has no value at those two asymptotes. So this one should say x is not equal to -2, x is not equal to 3. That brings us to the last one. The last one is going to be differentiable everywhere except for at this instant right here at 2. It has a vertical asymptote, and so it's not going to be differentiable there, so we'll say it's differentiable for all x values except x cannot be 2. So B asks us to name the functions for which they're continuous on their entire domain, but they're not differentiable, and those would be this one right here. So we know that the vertical tangent is an example of something that can make it continuous but not differentiable. And then the other example would be this one right here is continuous on its whole domain, but it's not differentiable at -1 because of the cusp, and that's the other thing that will affect it. I guess technically this one is not differentiable at 0, but because it's an endpoint, that's boring. We're not going to worry about that. The two interesting cases are the cusp and the vertical tangent. Come down here. Notice that this function, this is the function from 4, is continuous everywhere. But if we take the derivative has a fraction where the original function did not have a fraction. And because of that, notice that if we plug in 2, we get 1 over 3 times 2 minus 2 to the 2/3. Okay, and that's equal to 1 over 0, which is undefined. So since the function is continuous, but we can show that the derivative is undefined, that's our point. So that's it for part 2. I want you to go on to part 3. Now part 3 is the last 2 pages, and they're both going to deal with piecewise functions. So I'd like you to work through the first page of part 3. When you get to the bottom right here, jump to the next video and check your work.